Hello everybody, this is Dr. Ritu Singh from Basic Science Department, and today's topic of discussion is IR spectra. So IR means it is infrared spectra. This IR spectra is also known as vibrational rotational spectra. So it is also referred as vibrational rotational spectra, because in IR spectra we consider vibrational motions, and one vibrational change is always accompanied by a large number of rotational changes. So the spectra is also known as vibrational rotational spectra. Now radiations are they the form of energies, and energy is directly proportional to frequency, but it is inversely related to wavelength. So IR spectra is always expressed in terms of frequency, that is centimeter inverse. The range of IR spectra is from 400 centimeter inverse to 4000 centimeter inverse. So this is the main range. Apart from this, we are having near IR region and we have got a far IR region. Then IR spectra is given by molecules which have got permanent dipole moment, and that dipole moment changes when the molecule undergoes vibration. So this is a condition for molecules to give IR spectra. The molecule should have a permanent dipole moment, and this dipole moment should change when the molecule undergoes vibration. For example, if I have molecules like H2O, hydrogen, Cl2, HCl or carbon dioxide, out of these molecules, water, HCl and carbon dioxide, they have got a dipole moment which is going to change when the molecule undergoes vibration. One of the vibrations in carbon dioxide is IR inactive, that we are going to discuss it. So these three molecules, they have got permanent dipole moment which changes when the molecule undergoes vibration. So these three molecules are IR active molecules, whereas hydrogen and Cl2, they are inactive. So these are IR inactive molecules, whereas these three, they are IR active molecules. So IR spectra is given by molecules which have got permanent dipole moment which changes when the molecule undergoes vibration. Then IR spectra, the range is from 400 to 4000 centimeter inverse. It is expressed in terms of frequencies, it is not expressed in terms of wavelength. Then IR spectra is also known as vibrational rotational spectra. Why? Because one vibrational change is accompanied by a large number of rotational changes, and in case of IR spectra we are going to deal with vibrations in the molecule. Now if we classify the IR spectra based on the range which is given, then we have IR spectra is divided into three parts. So this is near IR region, this is far IR region. This starts approximately from 50 centimeter inverse and it goes to 667 centimeter inverse. Then the main IR region, this is the main IR region, this is IR region. It is divided into two parts, and the range is from 667 to 1400 centimeter inverse, and then to 4000 centimeter inverse. The last range of this is 12,500. So this is the division. The main IR region is divided into two parts. One is fingerprint region. This is fingerprint region, and from 1400 to 4000 is functional group region. Functional group region. So this is the division of IR spectra. So IR spectra is basically divided into three parts: far IR, IR range and near IR range. Now in case of far IR range, which is from 50 to 667, this here only rotational changes take place. So the molecule is having only rotational changes. So actually it is not considered in IR range. Now I told you the range is from 400 centimeter inverse to 4000 centimeter inverse. So this is going to vary. So it can be 4000 or you can write it 667. Some of the books it is 667, it is 4000, but this much variation is going to be considered. Now, so in far IR region only rotational changes are taking place. Molecule is not undergoing vibrations. In case of near IR range, some of the complex molecules or some of the complex compounds only they show vibrations, but the main range or the main IR region is this one. Now the main IR region is further divided into two parts. One is fingerprint region, the other is functional group region. Regarding fingerprint region, as two persons they do not have same fingerprint. Similarly, in case of molecules, two molecules they cannot have same IR spectra. So this region from 667, or I write it as 400 centimeter inverse, 400 to 1400, this region is going to give all the informations about the molecules, what are the type of vibrations, as we are going to discuss the types of vibration, then what kind of bond is there, whether the single bond is there, double bond is there, triple bond is there. So every bond is going to show absorption at a different wavelength. So actually this fingerprint region is a characteristic of a molecule. So this is a characteristic of the molecule. Characteristic means no two molecules can have same fingerprint region, or no two molecules are going to have same IR spectra. So that is why this range is important. Next we come to functional group region. Functional group region starts from 1400 to 4000. Now all the functional groups they show absorption within this range, and again for different molecules we have got different absorption frequencies. Like if I take alcohols, then we have got aliphatic alcohols, we have aromatic alcohols, then we have primary, secondary and tertiary, aliphatic as well as aromatic. So every type of alcohol is going to show absorption on a particular frequency. So that is functional group region, which is 1400 to 4000. So the main IR region is divided into two parts. One is fingerprint region, the other is functional group region. And if we consider both the things, functional and fingerprint, then it gives all the information about the molecule. So this is the classification of IR spectra. Now in IR spectra we can calculate the degree of freedom of a molecule. So the next is calculation of degree of freedom in a molecule. Degree of freedom means how much freedom is there for the molecules for any kind of movement. So degree of freedom, so total degree of freedom in a molecule is given by 3n, where n is number of atoms. It is number of atoms, and 3 refers to, we are going to consider three types of freedoms: translational, rotational and vibrational. So because of this we are writing this 3, and n stands for number of atoms. Now we have got two types of molecules. We have got a linear molecule and we are having a non-linear molecule. Suppose here we are going to discuss non-linear and here linear molecules. So we are having two types of molecules, linear and non-linear. So first I consider linear. translational degree of freedom is equal to 3. Translational motion means to and fro movement on an axis. So whether I consider non-linear molecule or I consider linear molecule, in both the cases the translational degree of freedom are 3. Translational degree of freedom is equal to 3. Next we come to rotational degree of freedom. Rotational degree of freedom. In case of non-linear molecule, the rotational degree of freedom is also 3, because we are having 3 axes on which the rotation is possible. In case of linear molecule, the rotational degree of freedom is 2. Why? Because if this is a linear molecule, when it is going to rotate on its axis, there is no change. So that is not considered. So rotational degree of freedom in case of linear molecule is 2. And from this I calculate vibrational degree of freedom. So vibrational degree of freedom in case of non-linear molecule is given by 3n, which is total number of freedoms minus 3 plus 3. 3 translational degree and 3 rotational. So it becomes 3n minus 6. So this is the equation for this is the equation for non-linear molecules. For linear molecules, the vibrational degree of freedom is given by 3n minus 3 plus 2, which is 3n minus 5. So if we know the molecule, if the molecule is linear or the molecule is non-linear. If we have a linear molecule, then vibrational degree of freedom are given by 3n minus 5. And if we have a non-linear molecule, then vibrational degree of freedom is given by 3n minus 6. Now, if we consider some of the examples, then if I take water, so it is a non-linear molecule. Water is having a band structure. So the degree of freedom, the vibrational degree of freedom is given by 3n minus 6, and n here is 3. So this is 3 into 3 minus 6. So this is 9 minus 6 is equal to 3. So water is going to have 3 vibrational degrees of freedom. Similarly, if we come to carbon dioxide, CO2. CO2 is a linear molecule. So because it is a linear molecule, so vibrational degree of freedom is given by 3n minus 5. So n here is 3. So 3 into 3 minus 5. So 9 minus 5 is equal to 4. So it is having 4 vibrational degrees of freedom. Now one thing in case of carbon dioxide, this is the structure of carbon dioxide. One of the vibrations in carbon dioxide is IR inactive, when this is the stretching. When it is pulled in both the direction, the resultant dipole moment change will be 0. So here it is IR inactive, otherwise it is an active molecule. And the third example, if we consider acetylene, again a linear molecule. So if it is a linear molecule, the vibrational degrees of freedom are given by 3n minus 5. So n here is 4. So 3 into 4 minus 5. So 12 minus 5. And accordingly, we can calculate the vibrational degrees of freedom. So vibrational degree of freedom can be calculated in case of linear molecule as well as non-linear molecule. If the molecule is linear, then the vibrational degree of freedom is given by 3n minus 5, and if the molecule is non-linear, then vibrational degree of freedom is given by 3n minus 6. So if we know that if the molecule is linear or non-linear, we can calculate the vibrational degrees of freedom. The next is types of vibrations. types of vibrations in IR spectrum. Then basically we have two types of vibrations. One is stretching and the other is banding. Now the basic difference between the two is regarding stretching, bond length is going to change but bond axis is going to remain same. So bond length is going to change but bond axis or bond angle remains same. It is not going to change. So this is stretching. And in case of banding, bond angle is going to remain same but bond length is going to remain same. Bond length is going to remain same, whereas bond angle or bond axis is going to change. So that is the basic difference between banding and stretching vibrations and banding vibration. Now the difference between stretching and banding, this is the difference between stretching and banding. Now when we come to stretching vibrations, then they are again of two types. So stretching vibration is symmetric stretching and asymmetric stretching. So the stretching can be symmetric or the stretching can be asymmetric. So if to explain, symmetric stretching means these are the three molecules. So either both the molecules are moving outward, or the second condition is the two molecules, they move inward. So either they are moving outward or they are moving inward. That is symmetric stretching. Now when we come to asymmetric stretching, here if these are the two molecules, these are two and this is one. So here it is moving upwards and here it is stretched. So one bond is stretched, the other bond is compressed. So this is stretching, and stretching is of two types: symmetric stretching and asymmetric stretching. In symmetric stretching, in case of stretching, what is happening? Bond length is going to change, whereas bond axis is going to remain same. Then stretching is of two types: symmetric and asymmetric. In case of symmetric stretching, either both the bonds are moving outward or they are moving upwards, or we can say one is stretched, the other is compressed. And in case of asymmetric stretching, one bond is compressed, the other is stretched. So here both the bonds are stretched or both the bonds are compressed. In case of asymmetric stretching, one is compressed, the other is stretched. Now if we consider stretching and banding requires more energy, so it is going to occur at a higher frequency. If we compare both the stretching vibrations, symmetric and asymmetric, then in case of asymmetric, one bond is stretched, the other is compressed. So here more energy is required in comparison to symmetric stretching. So asymmetric stretching occurs at a higher absorption frequency. So the frequency of absorption in case of asymmetric is more in comparison to symmetric. Now next we come to banding, and banding is again of two types: in the plane banding and out of plane banding. So what is happening in case of banding is bond length is same but bond axis is going to change. And again banding is of two types: in the plane and out of plane. In the plane banding occurs at a lower frequency in comparison to the out of plane banding. Then again, in the plane banding is of two types. The first in the plane banding is scissoring. The other is rocking. Scissoring means if these are the three bonds, then the two bonds, they are going to move towards each other or they are going to move away from each other. That is known as scissoring. Scissoring is the movement of bond is like a scissor. Either they are going to move towards each other or they are going to move away from each other. So that is scissoring. Rocking means the two bonds are moving in the same direction, either towards left side or towards right side or left side. So rocking means the bonds are going to move in the one direction, either right or left or right. And in case of scissoring, the bonds are going to move towards each other or they are moving away from each other, just like a scissor. So, and if we compare the frequencies of the two, then for scissoring we require higher frequency because bonds are moving in opposite direction. Then out of plane bonding. Out of plane banding is again of two types. One is wagging and the other is twisting. If we talk about wagging, then if these are the molecules and I write positive sign. So I am writing positive sign for above the plane banding and I am going to write negative sign for below the plane. So if the bonding is above the plane or the bonding is below the plane. If I am writing positive signs, that means the banding is above the plane, and if I replace this positive sign with a negative sign, then the banding is below the plane. So this is wagging. And twisting means, in case of twisting, one bond will move above the plane, the other bond is going to move below the plane. So this is twisting. So these are the types of vibrations which can take place in a molecule. So basically we have two types of vibrations, stretching and banding. The basic difference between the two, stretching, bond length is going to change, whereas bond axis remains the same. Whereas in case of banding, bond angle or bond axis is going to change, but bond length is going to remain same. Then when we come to stretching, we have two types of stretching, symmetric and asymmetric. In case of symmetric stretching, either the bonds are moving down or they are moving up or towards that, or stretched or they are compressed, but both the bonds. And in case of asymmetric, one bond is compressed, the other bond is stretched. When we come to banding, then we have got two types of banding, in the plane and out of plane. In the plane banding is of two types, scissoring and rocking. In case of scissoring means the bonds are moving towards each other, as I have shown, or they are moving away from each other. So the bonds are moving like a scissor, so it is scissoring. Rocking means the bonds are moving either towards right side or they are moving towards left side. Out of plane banding is again of two types, wagging and twisting. Wagging means either the bonds are moving up above the plane or they are moving below the plane, and in case of twisting, the bonds, one bond is moving above the plane, the other bond is moving below the plane. So this is all in types of stretching. Now to know how we are going to do this, suppose I have got this molecule, Br, then CH double bond CH2. Suppose this molecule is there. Now here, if I consider carbon-carbon bond, it is a single bond, it is going to show absorption on a particular frequency. Then I have to consider whether this is the bond is stretched or this bond is banding. Then if it is stretching, then whether it is symmetric or asymmetric. if there is a banding vibration, then it is out of plane or it is in the plane. If it is in the plane, then whether it is scissoring or rocking, and if it is out of plane, then it is wagging or twisting. So these are the combinations which can be possible, and this is done for every bond. So the structure is, that is how we determine the structure of a particular molecule. So either in questions, either this structure is given and you will be asked the frequency at which it is going to vibrate, or you will be given vibration frequencies and then you have to come up to this formula. So this is how we deal in IR spectra. Now we consider the vibrational spectra in case of IR. Vibrational spectra or vibration spectra. Now to start it, we first consider that the molecule is vibrating as a simple harmonic oscillator. Now if we consider to vibrate as a simple harmonic oscillator, that means it is vibrating with the same amplitude. Then the frequency is given by 1 over 2 pi under root k over m, where k is the force constant and m is the mass. Now if we consider the vibrating or the simple harmonic oscillator is a diatomic molecule, then this m can be reduced by mu, as we have done in rotational spectra. So this equation can also be written as 1 over 2 pi under root k over mu. So mass is replaced by mu because we are considering a diatomic molecule. Now here the frequency is in seconds. If we have to convert the seconds into second inverse, the frequency, the unit of frequency is second inverse. If we have to convert it into centimeter inverse, then we multiply, divide here by c, which is velocity of light. So to convert second inverse into centimeter inverse, I write 1 over 2 pi c under root k over mu. So this is the value of, or the equation of frequency, where k is the force constant, mu is the reduced mass and c is the velocity of light. Now so mu is equal to 1 over 2 pi c under root k over mu. Now potential energy of the vibrating diatomic molecule is given by 1 over half or 1 by 2 kx square, where k is the force constant as here and x is the displacement. So this is the equation for potential energy. Now if I solve Schrödinger wave equation for a diatomic molecule which is vibrating as a simple harmonic oscillator, then we get vibrational energy levels, and this energy of those vibrational energy levels is given by EV. EV is energy of vibrational quantized energy level, which is given by 1 V plus half h mu. So when the Schrödinger wave equation is solved for a diatomic molecule which is vibrating as a simple harmonic oscillator, then energy is given by this equation. Now the meaning of this energy is, suppose these are the vibrational levels. So this is 0, 1, 2, 3. So according to this equation, the lowest vibrational state is not going to have energy as equal to 0, but the energy here is half h mu. So the lowest energy state is going to have the energy of half h mu, and the energy difference between the two energy levels is constant, which is h mu. So this is referred by this equation of energy when it is calculated for a simple harmonic oscillator. Now, if I express this energy again in terms of centimeter inverse, then I divided by this equation by hc. So, the equation becomes V plus half mu over c. This mu over c is omega naught. So, we write this equation as V plus half omega naught. So, this is the energy equation of energy of quantized vibrational energy levels. So, the equation of energy is V plus half omega naught. Regarding selection rule, the selection rule here in case of vibrational when in vibrational spectrum is delta V plus minus 1. So, if I consider a transition from V to V plus 1, then energy is given by V plus 1 plus half omega naught minus V plus half omega naught. And if I solve this equation, then I get omega naught. So, this is the equation for energy when the transition is from V to V plus 1. Now, what we refer from this equation is the molecules, the maximum molecules, they are present in ground state, and the vibration which they are having is only stretching vibration. Bending vibration is not going to take place. So, when we consider a molecule to be vibrating as a simple harmonic oscillator, then frequency is given by 1 over 2 pi under root k over m, where m, because we have considered a diatomic molecule, so m is replaced by mu. If we express it in terms of centimeter inverse, then we divide it by c. C is the velocity of light. So, the frequency becomes 1 over 2 pi c under root k over mu. And if we solve the Schrödinger wave equation for a diatomic molecule vibrating as a simple harmonic oscillator, it is given by V plus half h mu. The significance of this equation is the lowest energy level is not having energy equal to 0, but the energy which is present is equal to half h mu. And the energy levels, different energy levels, they are equally spaced between, and the difference in the two energy level is h mu. Now, if we have to convert it in terms of centimeter inverse, then we divide it by hc, and we have arrived to this equation where the selection rule was considered, or the selection rule in case of vibrational spectra is delta V plus minus 1. So, when we show this transition, we arrive to this equation, and the meaning of this equation is that the molecules, most of the molecules, they are present in their ground state, and the vibrations which they show is a stretching vibration. They are not going to give bending vibration. So, this is inferred from this equation. So, this was the case when we considered a molecule, a diatomic molecule, to behave as a simple harmonic oscillator, but this is a very ideal situation. In normal situations, unharmonicity takes place. So, if we include unharmonicity, or if we consider unharmonicity, the equation of energy is going to change. So, for unharmonic oscillators, unharmonic oscillations, the energy is given by V plus half omega naught minus V plus half whole square omega naught x naught. Here x is unharmonicity constant. So, when we consider unharmonicity in the vibration of a diatomic molecule, then the equation of energy is this one, where x is unharmonicity. Now, when we were considering harmonic motions, then the selection rule which was given was delta V plus minus 1, but because now we have considered unharmonicity, then the selection rule is going to change. It will be either plus 3 or it can be plus it can be +2 or it can be +3, depending upon the amount of unharmonicity which has been introduced. And in case of harmonic oscillator, the energy levels, the difference between the two energy levels was same, but here it is going to be different. It will go on increasing. This will be the condition when it is an unharmonic case, and when it was harmonic, then the difference in the energy levels was same. This was the condition for harmonic, and this is the condition for unharmonic. In case of harmonic, the rule was ±1, and in case of unharmonicity, it can be either +2 or it is +3. So this is a difference between when a diatomic molecule is vibrating as a simple harmonic oscillator or it is vibrating as a unharmonic oscillator. The last spectra which we considered is vibrational rotational spectra. Vibrational rotational spectra. So, in case of IR spectra, the first we discussed as the molecule to be vibrating as a simple harmonic oscillator. When it was vibrating as a simple harmonic oscillator, then the selection rule was delta V ±1, and the energies were equally spaced. When we considered a molecule to be vibrating as an unharmonic oscillator, then the selection rule was ±2 or ±3, and the spacing between the energy levels was not same. It will keep on increasing. But if we consider rotational changes with vibrational changes, then the equation is given by Ej J plus EV. This is energy for rotational changes, and this is energy for vibrational changes. And whenever we consider the vibrational and rotational energies, or whenever we consider vibrational and rotational spectra, there the molecule is not going to vibrate, the diatomic molecule is not going to vibrate, or we cannot consider it to be vibrating as a simple harmonic oscillator. We have to consider a diatomic molecule to be vibrating as an unharmonic oscillator. So, if we write the two equations, I get Bj J plus 1, this is for Ej, plus V plus half omega naught minus V plus half whole square omega naught x naught. So, this is the equation when we consider vibrational and rotational spectra together. But by default, here delta J is ±1. But even if we are considering unharmonicity, even then the selection rule for vibration will be ±1. If we take unharmonic oscillations exclusively without rotation, then this rule is either ±2 or it can be ±3. But if I consider this unharmonic factor with the rotational spectra, then the selection rule for whether it is rotation or vibration, that is going to be 1. So, rotational spectra, the selection rule for rotational changes is ±1, and selection rule for vibrational change is also ±1. So, this is the condition when we have considered vibrational and rotational spectra. Now, if we draw this vibrational and rotational spectra, so here we have to consider V is equal to ±1 and delta J is equal to ±1. So, the transition is going to take place from V to V plus 1. So, this is V and transition is taking place from V plus 1. So, this is vibrational changes or vibrational spectra. Now, within vibrational changes, we are having rotational energy levels. So, the rotational energy levels are, this one is 0, then we have 1, 2, 3 and 4. So 0, 1, 2, 3, 4. So these are rotational changes within this vibrational energy level. Now if I have to, similarly I am going to draw, these are J, rotational energy levels. Similarly I am going to draw for V plus 1. So this is 0, then I have 1, then 2, 3, and then this is 4. This is again J. So this is for J plus 1. So we are having a vibrational changes, and within vibrational changes we are going to show rotational changes. So this is the vibrational rotational spectra. So delta J, the selection rule for rotational changes is delta J plus minus 1. So for delta J plus 1, the transition is from 0 to 1, then 1 to 2, then 2 to 3, then 3 to 4. This is the transition which is going to take place: 0 to 1, 1 to 2, 2 to 3 and 3 to 4. These transitions are for delta J plus 1. Then if I am drawing the transition for delta J minus 1, then I move from 1 to 0, then 2 to 1, then 3 to 2, and the last is 4 to 3. These transitions are from delta J minus 1. For plus 1, I am moving from lower energy state to higher energy state: 0 to 1, 1 to 2, 2 to 3 and 3 to 4. Whereas in case of negative, which is minus 1, I am moving from higher to lower: 1 to 0, 2 to 1, 2 to 3 and 4 to 3. So this is the rotational vibrational rotational spectra of a diatomic molecule. After this we have got applications. Regarding applications of IR spectra, the first thing, it helps us to calculate the force constant, which is given by mu is equal to 1 over 2 pi c under root k over mu. The force constant, we can calculate force constant. Second, it helps us to elucidate about the structure of the molecule. So about the structure means it is going to tell us about the bond length, it is going to tell about the bond axis of the molecule, molecular symmetry, then types of vibrations it is going to take place. It is going to tell whether the molecule is having a dipole moment or it is not having a dipole moment, and if it is having a dipole moment, then with the vibrational changes, is the dipole moment changing or dipole moment is not changing? Because if the molecule is IR inactive, that even if it is having a dipole moment, the molecule is IR inactive. That means dipole moment is there, but it is not changing with vibration. Then it tells us about what type of vibration is there, whether the molecule is having stretching or it is having bending. Then if it is having stretching, then what type of stretching is there, whether it is symmetric or it is asymmetric. Similarly, if it is having bending, then whether the molecule is bending in the plane or out of plane. And then if it is bending in the plane, whether it is scissoring or it is rocking, and if it is out of plane, whether it is wagging or it is twisting. So this is the information which is obtained by IR spectra, because IR spectra is characteristic of a molecule. No two molecules can have same IR spectra. So it tells us about everything about the molecule. Then it is also going to tell us about the functional group which is present, because every functional group shows absorption at a particular frequency. Then it tells us about the purity, or it helps us to identify impurity in the molecules. Now in case of UV spectra, whenever impurity is present, then the band which is obtained because of impurity is highly intensed. But here in case of IR spectra, if the impurity is present in the molecule, then every impurity is going to give an extra band. So, extra band is produced because of any kind of impurity, or any impurity is going to give the band, extra band. That is how we can determine the purity or impurity present in the molecule. And last is, it helps us to distinguish between the two types of hydrogen bonding, and it is the most important application of IR spectra. So, we have got two types of hydrogen bonding, intermolecular and intramolecular. So, if we discuss this, then now this molecule here, it can form a bond. This is intramolecular hydrogen bonding. Intramolecular means within the molecule. And if we consider the second molecule, OH and NO2. Now here internal bonding between OH and NO2 is not possible. So this is having intermolecular hydrogen bonding. So intra is within the molecule and inter is between the molecules. If these two compounds are diluted, then what happens is, the absorption band which is obtained because of intermolecular hydrogen bonding will get diminished, whereas the absorption band which is obtained because of intramolecular hydrogen bonding is unaffected. The reason is, even if we are going to dilute it, hydrogen bonding is not affected, because it is not, hydrogen bonding is present within the molecule. But in case of intermolecular hydrogen bonding, the absorption band goes on becoming it will diminish, it will become weak, because here when we are going to dilute the molecule which is having intermolecular hydrogen bonding, the bonding is going to take place between OH and water molecule. So this is how we can distinguish inter and intramolecular hydrogen bonding on the basis of IR spectra. So if I summarize the IR spectra, then IR spectra is also known as vibrational rotational spectra. Why? Because one vibrational change is accompanied by a large number of rotational changes, and it is given by molecules which have got permanent dipole moment, which changes when the molecule undergoes vibration. Then the range of the main IR region is 400 to 4000 centimeter inverse, and this range is also divided into two parts, IR fingerprint region and functional group region. So fingerprint region is going to give all the information about the molecule, and what is the functional group is given by the functional group region. No two molecules can have same IR spectra. Then by IR spectra we can calculate the vibrational degrees of freedom. If we have a linear molecule, then vibrational degree of freedom is given by 3n minus 5, and if the molecule is non-linear, then it is given by 3n minus 6. Then we have types of vibration. We have got two types of vibration, stretching and banding, and then we have got different parts of stretching and banding. Then we have discussed about the vibrational spectra. If we consider a molecule to be, a diatomic molecule to be vibrating as a simple harmonic oscillator, then the energy is given by V plus half omega naught. And the selection rule which is followed is delta V plus minus 1. If we consider unharmonicity, then the energy is given by V plus half omega naught minus V plus half square omega naught x naught, and here the selection rule is either plus minus 1 or it is plus minus 3. And then we have considered vibrational spectra with the rotational spectra, and then the equation was Ej plus EV, and here the selection rule for is delta J plus minus 1 and delta V plus minus 1. And the last we discussed about the application of IR spectra, where we can calculate force constant, we can talk about we can identify the impurities which are present in the molecule. Then it helps us to elucidate whole structure of the molecule, and last and the most important one is it helps us to distinguish between inter and intramolecular hydrogen bonding. So this is all in IR spectra. Thank you.